You might remember finding the limit of a function from your previous math course, and the good news is that most of the time, you can find the limit of a sequence in the same way that you find the limit of a function. For example, if you look at the sequence down here, well, this sequence, this is just 1 over 2 to the n, 1 over 2 to the n, where n goes from 1 all the way to infinity. So then I can think of this sequence 1 over 2 to the n as a function as well. So I'm gonna change the variable from n to x here just because we are more familiar with functions in terms of x. So here I just change my n to x and here is my function, and now I can find the limit of this function 1 over 2 to the x when x goes to infinity. To find the limit of this guy, well, there are many ways we can do that, but let me just sketch the graph of this function. 1 over 2 to the x looks somewhat like this, and as you can see, as x goes to infinity, the value of my orange function is kind of keep decreasing and it's coming down to 0. So this limit is gonna just equal to 0. So what that means is, if I look at the limit of the corresponding sequence, the limit of the sequence, the limit of a sub n when n goes to infinity is also going to be 0 as well. So basically, we can find the limit of a sequence by pretending that it is a function. And the way this works is that if the limit of a function is equal to something, where that something, it can be a real number or it could be plus or minus infinity, then the limit of the sequence is also going to be the same thing. So let me kind of write to the side here. If the limit of my f of x when x goes to infinity is just some number, let's just say it's a number a, then what that means is the limit of my sequence. What that means is the limit of my sequence, the limit of my a sub n where n goes to infinity is also going to be the same thing. And this works when this is plus or minus infinity as well. So I'm just going to go ahead and copy and paste this because it's just the same thing anyway. If the limit of our function is infinity, then the limit of my sequence is also going to be infinity. And if the limit of the function is negative infinity, then the limit of the sequence is also going to be negative infinity. Okay, if this is minus infinity, so let me kind of clear some space here. If this is minus infinity, then the limit of the sequence is also going to be minus infinity. Okay, so let me do the next example now. Our sequence is n over n plus 1. So once again, I'm going to pretend that this is just a function. So my f of x is just going to be x over x plus 1. So now, I want to find the limit of x over x plus 1 when x goes to infinity. Now, there are many ways we can do this, but let me just do the usual method. I can divide both the numerator and denominator by x. So this limit is going to just equal to the limit when x goes to infinity of x over x divided by x plus 1 over x. So here, the value of the term behind the limit doesn't change because I divide by x both to the numerator and denominator. Now then, if I were to simplify this thing, the numerator x over x is just going to be 1, and the denominator x plus 1 over x is just going to be 1 plus 1 over x. Now, when my x get really large, 1 over x, this term here, is going to get really small. So when x go to infinity, 1 over x is just going to go to 0. So this whole thing is going to be just the limit when x go to infinity of 1 over 1 plus 0. Which is gonna be just equal to 1. So here I have that the limit of the function is 1. So now I can conclude that the limit of the sequence is just gonna be the same thing. The limit when n go to infinity of a sub n is just gonna be 1. Okay, let's look at the next one. For the next one, our sequence looks a bit complicated. We have log of n over n squared. So here my function is just gonna be that I change the same, it's gonna be the same thing, I just change the variable n to x, just so we are more familiar with the function in terms of x. So now, I would like to find the limit of log of x over x squared when x goes to infinity. Now, if we try plugging in x to be infinity, we're going to have log of infinity over infinity squared, which is infinity over infinity. But now, because we view the limit of a sequence as the limit of a function, and that means we can also now use the L'Hopital's rule, which basically states that if we are trying to find the limit of a fraction here, if we are trying to find the limit of a ratio of something and then both the numerator and denominator, if they are both 0 or if they are both plus or minus infinity, then we can take the derivative of the top and the bottom separately and find the limit of the resulting derivatives instead. So if I want to find the limit of this ratio log of log of x over x squared, that is gonna be the same as just the limit of their derivative. So I take the derivative of the numerator, the derivative of 1 over x is just gonna be, derivative of log of x is gonna be just 1 over x. And the derivative of x squared is just gonna be 2x. Okay, so this is the result of using L'Hopital's rule. I can simplify this 1 over x over 2x is just gonna be, let me see, this is just gonna be 1 over 2x squared. And now when x get really large, 1 over 2x squared is gonna get really large as well. 1 over a really large number is gonna be just 0. So that means by L'Hopital's rule, I can conclude that the limit of this function is gonna be 0. So that means the limit of a sequence a sub n is gonna be 0 as well. So this thing equal to 0. Okay. Now, there is actually one exception to what we have talked about here actually. So if the limit of the function, if it's a number, then the limit of the sequence is a number. If it's infinity, then the limit of sequence is infinity. Or if the limit of the function is negative infinity, then so is the limit of a sequence. However, if the limit of the function, if this thing does not exist, if the limit of a function doesn't exist, then I can't conclude anything. So if the limit of the function does not exist, then I can't conclude anything about the limit of a sequence. This is going to be what happens in the last example here. If I want to find the limit of this sequence, let me actually kind of move this thing to the side a little bit because it gets in the way. Hello? Oh, okay. Alright. So if we look at this as a function, so I'm gonna be looking at the function sine of pi x. Now the graph for this guy look like this. So when x go to infinity, this graph, so it's just like it's gonna be have just like the graph of a sine function. So the value of my function keep go up and down. It doesn't approach a certain value. So I can say that the limit of the function does not exist. So in the case that the limit of the function does not exist, then I can't conclude anything about the limit of the sequence. So that doesn't mean that the limit of the sequence will not exist as well. So we have to actually look at the value of the sequence now. But if we actually take a look at the numbers in this sequence, so if I try to plug in several values of n, so the sequence is gonna be just sine of pi times 1, sine of pi times 2, sine of pi times 3. So here, notice how the sequence is just the sine of pi times n, and my n go from 1 to infinity, so it's just gonna be pi times 1, pi times 2, pi times 3, and so on. Sine of pi times 4, and so on. It turns out that the value of sine of 1 pi, the sine of pi is just going to equal to 0. Sine of 2 pi is 0. Sine of 3 pi is 0. Sine of 4 pi is also 0. So it turns out that this sequence is actually just a sequence of 0. The value of all the numbers that we see here are going to be 0. So the limit of a sub n, when n go to infinity, is going to be 0. So here, whenever we try to find the limit of a sequence, we can kind of pretend that it is actually just a function. So if the limit of a function is anything, we can conclude that the limit of the sequence is just the same thing, except when the limit of the function doesn't exist, then we can't really conclude anything.